Welcome to Network Analysis. I'm excited to be here and to present to you what is going to be UIC's #1, first of its kind, Network Analysis course. My name is Sasha Goodfriend and I'm going to be your instructor today. We are going to have a very unusual lecture for the first lecture. It's going to be recorded, so you will hear me talk for about an hour. That's going to be the first lecture. The subsequent lectures are going to be in class. So let me tell you a little bit about the mechanics of the course first. The regular classes are going to be happening on Fridays from 10 to noon in the School of Public Health building, SPHPI, in room 1001, that's the 10th floor. After that class, we're going to have regular office hours. So it's going to be Fridays from noon to 1. Or you can shoot me an email and we would meet and I will try to answer your questions about network analysis. That's the basic mechanics. The course is aimed to senior undergraduate and graduate students, and I hope also we are going to have people coming in just to listen and to enjoy this wonderful discipline of network analysis. Like I said, it's the first course of its kind, so there's going to be a lot of exciting material. You will have opportunities to explore and apply the techniques of network analysis. So I will show you some of the basic techniques, I will show you some software, and then from that you can proceed and use them for your research. Use them for exploring networks, whatever networks you're working on. Some people in the class are going to be doing epidemiology, some people are going to be doing engineering, some people are going to be doing computer science. Whatever area you're in, I'm going to show you the techniques that you will need to explore networks. Some of the lectures are going to be quite mathematical, not this one. This one is going to be fairly introductory. I hope to give you a sense of what is so important about networks. But other lectures are going to be pretty advanced mathematical, so prepare to take notes and prepare to look at matrices and look at some operations and look at some statistics. And that's the plan. We're going to meet once a week for about 10 weeks. We're going to have an interesting guest lecture by my colleague in epidemiology, Basmati Budra. We're going to really cover a broad spectrum of topics. We're going to also look at different types of network analysis software. So one of the things that you have to do for next class is to install some of the basic software we're going to use in the course and make sure it's working. So without further ado, let's turn on to some network analysis. There are 3 basic questions that I would like to address in today's lecture. The first is, what are the 2 basic elements of any network? So there's many different kinds of networks, but all of them have those 2 basic elements. I will also tell you a little bit about the history of network analysis as a discipline, how people got interested in this area, and what are they doing now. Give you an overview of what's happening in this area. And finally, I'll tell you about some of the stuff that's happening today in network analysis, some of the really interesting work that's been happening. You will also get a sense of some of the software that's available. 2 particular software package. One is called Gephi. It's a cross-platform software for visualization of networks, so you can do graphical exploration of a network. And then you're going to also, I'm going to also hit on using R for network analysis, and this is something that we'll use later on. So for next class, you're going to I'm going to ask you to install Gephi and R, and also play a little bit with Gephi. Maybe I'm a mathematician, but I love starting everything with a definition. So network consists of 2 sets, namely 2 collections of objects. And there are 2 related collections of objects. The first one are N. N is called the node. Nodes are the elements on which a network is built. So typically nodes are people. So in a social network, that will be people. In the epidemiology network, that will be people. But nodes could also be something else. Nodes could be, for example, computers that are connected to each other. And so the set of all the computers that are connected to each other is going to be a set of nodes. There are also a second element of any network that's called the edges. Edges are pairs of nodes without distinguishing order. So you have here an example of a network consisting of nodes A, B, C, and D. And the nodes this is N. What are the edges in this network? Well, if you look at this network here, you're going to see that the edges are A to B, A to C, and then C to D. So there are 3 edges in this network and 4 nodes. What is called nodes is sometimes called by other names. So very commonly nodes are also referred to as vertices. So there's one vertex and multiple vertices. Edges are also given different names. So sometimes they're called arcs. Although arcs sometimes tend to mean collections. Arcs means edges with direction. So you go from A to B, but you don't necessarily go back from B to A. So edges are kind of like arcs, but they tend to refer to directionality. They're also called connections, linkages, ties. These are all synonyms for the word edges. We're going to focus in this lecture on unordered pairs. So it means that if A is connected to B, B is connected to A. That's the simplest kind of network. It's also, this type of network is called a simple graph in graph theory. There's also more sophisticated networks, but the most sophisticated kind of networks are often viewed as an extension, are an elaboration of the basic scheme. So all networks have nodes and edges, but they sometimes have additional features. And I'll talk about some of those additional features soon. Now, there's another term that's very obscure, but very important for a lot of network analysis, and that's the degree. So the degree of a node means the number of connections that it has, or to be specific, the number of incident edges. So you can see here that node B has 1 incident edge, namely B is connected to A, so the degree of B is 1. Node A has 2 incident edges, so A is connected to B and to C, so it has degree 2. So essentially degree is a measure of how important a node is. It's a very simple measure of how important it is. You can essentially look at the person, find out how many friends he has. So that's a basic measure. Certainly, like if you look at, say, rock singers and you find out how many followers they have, that's a rough indication of how significant they are. Now, whether it doesn't say that the music is good, it just means something about, it's a crude measure. So it's a crude measure. So I imagine that there are rock singers who have lots of followers on Twitter, but the music is pretty bad. And I'm sure you can come up with examples of that. So a network has 2 parts, nodes and edges, and there's also some related term that's not, but that's a property of any network, which is a degree. So we can look at any node in the network and say the degree of that node is 1, 2, or 3. So nodes that have degree 0 are nodes that have no friends, and those are sometimes called singletons. So that's a situation that does not actually happen in our network here on the bottom. So there are no singleton edges. Singleton nodes, I'm sorry. So degree only belongs to a node. All right. Now, network analysis in general is a discipline. It's a paradigm. See, network analysis says that whenever we are studying something, we would like to look at it from the point of view of the relationships. Let me repeat that again. So network analysis is a scientific paradigm based on analysis of relationships in the system. In a sense, a lot of biostatistics is different from network analysis, because in a lot of biostatistics, in a lot of statistics in general, we are focused on individuals, their properties. So we can look at people and look at their genders, we can look at when they were born, their race, their ethnicity, how frequently they do a certain activity, how healthy they are. But network analysis says, focus on something else. Network analysis says that you should focus on the relationship between people and not so much on their properties. Of course, those two perspectives are complementary. But in this course, we are really trying to understand relationships. How to study relationship between people. What can relationships tell us? In a sense, we are looking at the system in the way it's composed, and the way the system was linked together, and not at the individual pieces. And this is a very powerful paradigm. Network analysis essentially is a paradigm that allows us to look at the world from a different perspective, a perspective that's different from most of statistics. And it's been tremendously successful. Almost any discipline you can name has been significantly impacted by network analysis. From history to archaeology, to literature, to English, and of course, endless technological things. We would not have internet today if people have not been thinking about networks, because an internet is a network. We would not have sociology today, modern sociology, without network analysis. It's a tremendously powerful perspective. In a sense, in every scientific paradigm, we emphasize certain things and de-emphasize others. So in network analysis, we emphasize the relationships. But in other disciplines, we emphasize the properties of the individuals. So in this course, we're going to look at the reality in a different set of spectacles. We're going to emphasize the relationships. This is really important. The traditional things, the traditional way of how people look at data has been at relationships in, for example, a Cartesian or time series data. So Cartesian data is a data in which you have a set of points and all of them have a certain covariance. There could be some non-Cartesian coordinates there, but essentially you look at points and their properties. Or sometimes people look at time series data. So that could be, say, the temperature in a particular area, or some kind of a variable like popularity of something. In network analysis, we are going to be looking at relationships. And the reason that network analysis is so powerful is because most complex systems could be represented as a collection of entities and their relationships. Let me say this again. Most complex systems, essentially most of the real world, could be studied as a collection of entities and relationships. That's why network analysis is so powerful. And that's why it gets its own course and sometimes multiple courses. That's why there are journals dedicated to this discipline. It's a cross-cutting theoretical paradigm. It comes with its own methods that you can apply to any area where you're studying networks. Let me pause here for a second. Wonderful. So we are 15 minutes down in the lecture. And now you should have a sense of what a network is and why is it potentially so powerful. I'm going to now walk you through a couple of examples of networks. On the left, you see here a typical situation. This is known as an egocentric network. You see a red node in the middle. It represents a single person. The person might be, for example, a person on Facebook. And that person is not indicated by any name. You see, it's just a node. Well, all you know is what are the relationships of that node. We know that person's connections. And you also know who of those friends are connected to each other. So you can see the person's friends and how the friends are connected. You don't see anything beyond. That's why it's called egocentric. So you're focused on a single person's, his relationship, and how is the relationship they're connected. This is a typical kind of object studied in sociology. Sociologists notice and focus on, for example, the existence of mutual friendships. So you can, if you look at the two nodes at the top left, you can see that they're both friends with the red one, and they're friends of each other. And sociologists note that social networks, as opposed to other kinds of networks, have a lot of that kind of triangles. They call this triads or triangles. They say that social networks are characterized by the existence of multiple triangles like this one. That's a typical kind of a sociological network. In epidemiology, we often study similar kinds of networks because epidemiology is interested in diseases, typical diseases of humans, and how people are connected is important. But we have a slightly different set of questions, and we look at some with different types of structures. So on the right, you're seeing here how an outbreak of influenza spread in a school. What is different about this kind of network is that people in that school are not necessarily close friends. What connect them together is that they happen to be in the same room and they infected each other. So that's a network that's overlaying friendship networks, and it's different. So some of those people are not friends of each other, some people are friends with each other, some people are relatives of each other. Nevertheless, there was an infection that spread through them, and that's the network you're seeing here is a contact tracing network. You're seeing here an initially infected adult, the person who was initially infected, and then the infection spread to another adult, and then it reached into a teenager. That's the blue one. And from that teenager, just keeps spreading and spreading and spreading. One of the things you're looking when you do this network, one of the things you notice is the degree. Degree is very important. You can see that in this network, the degree varies quite a lot. So the first person, what was his degree? Remember, the degree is the number of connections that you have. The first person's degree is 1. So that person has 1 connection. In fact, the second person in that network, the second person in the chain of transmission, in this transmission tree, had degree. Well, it depends how you define degree. So now there's a little bit of subtlety. Notice that in this network, you have errors going around. Those errors have direction. So in such networks, we distinguish between 2 types of degrees. There is an in degree and out degree. So you can see that the first person had 0 in degree and 1 out degree. The second person had 1 in degree and 1 out degree. The third person was a disaster because he has 1 in degree, but he has 1, 2, 3, 4 outgoing connections. So he infected 4 other people, and so his out degree is equal to 4. So that person was a major disaster because from him the epidemic spread out to a lot of other parts of the school. You can see here that by talking about degree, we can immediately say which persons were important, which people were not important. It's interesting that in this network, all the in degree is 1. So all of the nodes have an in degree 1. And that's an interesting characteristic. Why do you think that all the nodes have in degree 1? It's a kind of think about this. Why is it that in the contact network for influenza, all the nodes have in degree 1? It doesn't. In general, in a directed network, you don't necessarily have all the in degree equal to 1. Well, the reason for that is very characteristic of epidemiology. You can only infect a person once, at least in a single season. Typically, the person will kind of disappear from the population until he recovers from the disease. So every person only gets infected once. And then that infection is kind of the most important infection we track. That's infection that we see. I think that it's possible that the person might get multiple exposures and both will be transmissible. But the reason he will kind of become sick will be because of the first infectious exposure. So all the in degrees is 1, and then the out degree varies a lot. Some people become very significant because they have high out degree. They infect lots of other people. Some people are low degree and they might infect nobody. I can see a lot of nodes which are sort of dead ends. Sometimes those nodes are called leaf nodes. They're kind of hanging off the tree. They're leaves. Finally, let's look at this other network at the bottom. This network actually represents the route of an airline. And what's striking about this airline is that Denver. Denver is super important to that airline. Denver is the place from which most flights originate. Probably for that airline, most of the flights are coming from Denver and they're going back to Denver. That's not always the case. So you can see that it flies from Denver to Seattle, and maybe from Seattle it can fly to Los Angeles and then back to Denver. I wouldn't be surprised if this is actually Frontier Airlines. I think in fact, Frontier flies to Midway, and I think it just goes back to Denver. So that's a typical network that you see for networks of supply chains in general. So that's a very important area of network analysis, looking at systems that are engineered, systems like transportation systems, like supply chains, from factory to another factory to consumers. Various internet looks a lot like this airline network. You have connections from point to point to point. Notice that it looks quite different from the social network, for example, and also from the epidemiological network. Yes, you still have nodes and you still have edges, but what are some of the differences? It visually looks different, but we want to point out some differences. Well, one difference that I would like to point out is the fact that it's not directed. Unlike the epidemiological network, here we are connecting nodes if there is service from one node to the other. So in reality, there could be situations where there was only one flight one way and not the other way. But typically, there's going to be, most of the flights will be bidirectional. So if you fly from Seattle to Los Angeles, there might be a flight going also in the opposite direction. So certainly in this diagram, you're not seeing any distinction between one direction and the other. That's a commonality with the sociological network. But it's very interesting that in the sociological network, there's not many leaf nodes. In fact, there's no nodes that have degree 1 in the social network. But in the airline network, there is a lot of nodes that have degree 1. For example, Chicago is a node of degree 1. St. Louis is a node of degree 1. Then Denver is sometimes called a hub. It's called a hub for a variety of reasons, but from a network analysis point of view, we see that Denver is a hub because it has such a high degree. A lot of network analysts use the term hub to say a node that has very high degree. That's a situation that occurs in a lot of technological networks. Cartoon network, is that a network? Well, it's a kind of a network because lots of people are watching it, and so Cartoon Network can be viewed as a node to which a lot of people are connected. But it's not really a network in most other senses. Why? Because it's hard to identify nodes, and it's a bit of a trivial example. So I don't think that there's no. Well, I mean, I think it would be a really stretch to call it a Cartoon Network. So Cartoon Network and network in our sense. Remember that a network has to have nodes and it has to have edges. And I don't, you can certainly say that it's a network, and sometimes people abuse this and they say like pretty much everything is a network if you look hard enough. But I don't think that there is really a relationship of the kind that we see in social networks, transportation network, and epidemiologic networks here. So the lesson here is that not everything that is a network is actually a network in our definition. Now, I mentioned to you that there is a lot of extras that are found in networks, and most networks indeed are not just nodes and edges. So common situations that happen in networks are what I would call annotations. So typically we distinguish between types of nodes, labels of nodes, sizes of nodes, and we also have edge annotations like directionality, signs, and also weights. So remember in the epidemiological network, yes, we have a relationship between people, but we also distinguish with different types of people. Some are adults and some are teenagers. We also distinguish between different states in epidemiology. Some people are, so this is a typo, so it should say infected versus not infected, maybe susceptible but not infected, vaccinated nodes versus not vaccinated nodes. Of course, we distinguish between sizes, and sizes could be defined in many different ways. So we can distinguish size based on edge, on the age of a person. So that's a type of size. For me, size is anything that is a real number. The age, the cost is a quantity like size. Edge annotations are very similar. So simplest edge direction annotation is directionality. So we sometimes draw an arrow to say X goes to Y. So that's a directed edge. And when X infects Y, that's a directed relationship. So X, the situation where X infects Y is different from the situation where I infects X. There's also a sign. So that's very interesting in sociology, for example, because when we say that X likes Y, that's different from when X dislikes Y. It seems like there is a directionality, but there's also this additional property of, is it a good relationship or a bad relationship? And sometimes there's also some kind of quantity, of weight that we can assign to edges. So X not just buys Y, but also buys a certain amount of Y. So here are some of the extras that are happening. Nevertheless, in all of the situations, we have the underlying network, nodes and edges. Those are just the extras that people annotate. In the basic network analysis paradigm, we are only going to be focusing on nodes and edges. Now, those annotations are going to be very application specific, as you can see. With the network, the type of network you're looking at is going to have different annotations and different edge annotations and node annotations. So the most common elements of all of this network analysis paradigms is the focus on nodes and edges and their relationships. Nothing else. That finishes the first part of my lecture. Thank you, guys. And there's going to be a link to get to the second part.